We're going to spend the next hour talking about big data, artificial intelligence, machine learning, and things of that ilk. My name's Alan Weil. I'm editor-in-chief of Health Affairs. We're the leading health policy journal in the United States. We did an issue on big data a few years ago and just a couple of months ago on precision medicine, very much related. And there's more than 50 minutes worth to talk about, but we'll do what we can in the 50 that we have. I'm joined by Lizzie Dorfman, technical program manager at Google Brain, Seth Berkley, CEO of Gavi, the Vaccine Alliance, Jake Komarneni. I thought I had it, and I apologize. Jake Komarneni, chair of the Human Diagnosis Project. And what we're going to try to do in this time is spend just a couple of minutes getting the language straight. This is an area maybe some of you aren't that familiar with. I'm going to ask each of my speakers to give a little bit of a use case so you can understand what the applications are. And then we're going to spend most of our time on what are the challenges, what are the issues around using data to solve problems, and then we'll close with a little time to look at opportunities, and we'll bring you into the conversation. I'm going to ask Lizzie to set the stage for us real quick. Big data, artificial intelligence, machine learning, what does this all mean?
Happy to. Let's start with big data. At its core, these are data sets that are so large that we've had to develop new capabilities to collect, store, transmit, and analyze them, largely computational and storage capabilities. Artificial intelligence, which is a term that is getting used quite frequently, means computers that have learned to perform tasks that typically require human-level intelligence. These are things like visual perception, translation, and speech recognition. Artificial general intelligence, I think, is important to differentiate from focused intelligence. So general intelligence would be a computer that could perform any human-level intelligence task. This is the stuff of science fiction. This is not possible today. This is not something we are remotely close to being able to do anytime soon. What we are close to being able to do, and in fact we actually have many examples of, is more focused applications of computers that have been taught to meet or even exceed human-level performance for specific tasks. So this would include things like the games of chess and of Go. So how do computers become intelligent? AI as a term has been around since the 1950s, and historically we have programmed computers to follow explicit rules. If A, then B. If C, then D. In the 1970s, however, a new set of methods that are collectively referred to as machine learning were developed. And these are methods that do not require that you pre-program a computer to know exactly how to process and handle information. These are methods that allow you to show a computer examples of the data that you're interested in and have the computer develop its own methods for doing the classification or prediction task that you're interested in. So in essence, machine learning methods are one way that we develop artificial intelligence.
I dare say that's the most succinct explanation of some very complex phenomena. I think we are off to a good start. I appreciate it. Okay, so now let's get into how does this fit with our topic here of health. And as I say, what I've asked is our three speakers operate in very different domains. And I've asked each of them to give you one example, although they each could give you many, of how these concepts play out in the work that they're doing. And once again, I'm going to ask Lizzie to start off because we have a little progression of different kinds of approaches that I think makes the most sense if you begin. So
sure.
Take us.
So I'm here from Google Brain, which, contrary to what it might sound, is not a neuroscience-focused part of Google. Brain refers to deep learning, which is a specific machine learning method. And my team is focused at the intersection of genomics and deep learning. We're very interested in understanding what problems in genomic might be amenable to these technologies and to see if we can develop applications that demonstrably exceed the status quo. So the first problem that we went after is related to how do we develop the most accurate sequencing tests possible. And I think it's actually a common misperception that when you order a genomic sequencing test, the information that comes off of the sequencer is a faithful, accurate, definitive record of your 3 billion bases organized into 23 chromosomes. That's actually not how it works. So I'm going to use an analogy that I think is a little bit more broadly accessible than the nuts and bolts of what actually happens in a sequencer. But to sequence a human genome, imagine that you had a paper phone book that had 3 billion letters in it, and you wanted to digitize that accurately. So if your process would involve taking 30 copies of that phone book, shredding it so that you had fragments of paper that had 100 letters on each of them. And if you think about it, 3 billion letters per book and 30 books, that's 1 billion pieces of paper. And you scanned each of those fragments of paper, and you knew that in the scanning process, 1 in 10 fragments of paper was actually going to have some type of an error that was artificially introduced. And now what you have is 1 billion scanned pieces of paper for which you know that there's errors that you have to correct for. And in essence, this is the core computational problem with working with the raw data that comes off of a sequencer to reconstruct the definitive true genome for the individual who is being sequenced. This is a long-standing problem that people have been working on for quite some time. We were interested in whether we could recast this as a machine learning problem. And in fact, we did so. And about 6 months after we did this was in 2016, the FDA launched the Precision FDA initiative. This is a public challenge to stimulate innovation in the community. And their focus was how do we improve the consistency and accuracy of sequencing tests. We believe this is critical to actually achieving some of the promise of personalized medicine through sequencing technologies. We entered our tool, which we named Deep Variant, and it won highest accuracy. And this shocked the competition because it was a completely novel methodology and a very rigorous evaluation that had been externally defined. Since then, we have actually lowered the number of errors by another 50% and released this tool as open source, publicly available technology, so anybody can access it and run it. So we did this as a proof of concept to convince ourselves, can we actually even think about how to frame genomics problems for deep learning, and can we convince ourselves that there's gains here? And our results so far with Deep Variant have really convinced us to invest in more problems in genomics.
Great. Jay, you're operating in a different environment. Why don't you give the audience an example of how you see big data in use?
Sure. So I think a lot of us get caught up in thinking about the implications of big data, AI, et cetera, in clinical care, which is tremendously important and very exciting, of course. But there are also very interesting ways in which AI can play a role in solving many of the problems in healthcare today that aren't just associated directly in the patient care path. So one example is today we are actually using machine learning and AI-based methods to reduce the burden of many kind of requirements that are causing physician burnout. So one of those is clinical documentation. So if you can actually make that significantly faster by using technologies like natural language processing and speech to text. A second area is basically taking processes like maintenance of certification or continuing medical education or peer review, other requirements that are required to be done by physicians and are really done manually and offline. A lot of that can actually be automated through the process of essentially just them interacting in a given clinical encounter. And then the third area is really around personalized learning and training and education. So if you think about the fact that today, we literally have no sense of which people know what about what. So we don't know if a community health worker in Rwanda performs relative to a physician in the EU versus a nurse in the US. We have no baseline for actually comparing clinical knowledge. And so really what we've focused on in conjunction with researchers at Hopkins and the NIH is actually developing an approach to measuring clinical reasoning through machine intelligence. So basically, as physicians from around the world create and solve cases into the Human Diagnosis Project, we can actually look at the individual ways in which they solve cases and create a very refined sense of their accuracy, their efficiency, their breadth of knowledge, and their depth of knowledge in a quantitative, objective, and scalable way that we can do from them actually participating in short case-based simulations a couple minutes from your mobile phone. So those are kind of some interesting areas that I think.
And Seth, you're out in the field trying to deliver vaccines. And what are the applications that you see for artificial intelligence?
So thanks, Alan. And Alan and I are the outsiders, and we have the computer brainiacs on either side. So I'm a use case person, and what's the challenge? We provide vaccines to 60% of the world's children, and I live in the land of bad data. So let me give you a current example. So you all know there was an Ebola outbreak recently, and we were the people that had made sure there was an Ebola vaccine available. Started out in a rural area, it then leaped into the provincial capital of Bandika. Bandika, how big is Bandika? Well, turns out the last census was 1984. And the estimates I heard were 300,000 to 1.5 million people. That's a big difference in terms of the potential risks and issues there. So we live in this land of bad data all the time. And what our goal is, ultimately, is to try to immunize every child. A third of the children in the world don't have birth certificates, aren't registered, so they don't exist. And so the challenge is, how do we turn that around using technology? So we have massive data sets in terms of the number of immunizations that occur, the number of locations. We have old census data. We have geospatial locations of people in villages and others. And what we've begun to do is work with different groups who can use big data techniques to triangulate data sets, to put data sets together that really don't fit together and that are dirty, but to use those to help us learn. And then our role is to go back and to try to create more accuracy, not the same type of testing you're doing, but go to a community and say, all right, here's what you've predicted through these techniques. How do we then use this? And if we can get it better and better, can we use this data to actually implement better programs on the ground? So we're here to learn.
Great. So Seth, you've teed up the issue of data quality. That's not the only dimension of data concerns. And what I want to do is to move into the segment where you now have a sense of what some of the potential is, but there are also some rough spots here. So from data quality comes data how representative the data are, data privacy, and ownership. And I wondered if either of you who are working a little more closely in this space want to comment on those or other challenges. We're going to get a whole bunch of them out on the table. Who wants to start?
Yeah, so that's a really important question. The first problem is that most data is not captured deliberately. And the design to actually capture such data is not actually being used to accomplish the end goal that data is being used for. As an example, we are taking existing data sources that were captured almost as data exhaust for a completely different purpose, such as clinical documentation in electronic health records is primarily a coding and billing system. So if we're trying to use that information to learn upon, there are several major problems. And I'll specifically give you an example with electronic health record data, but these problems apply to many forms of data that we don't capture deliberately. Number one is a lot of the information is highly unstructured. It's unverified, so we don't know that it's true. We just know it's what that clinician said. It's very low signal to noise. So you have many findings or observations in such a system, but very few of them are actually relevant to the clinical encounter. It does not capture the thought process of the person who's making decisions. It only captures what they ultimately did. And it is highly overrepresentative of the sickest patients. So if you're building models off of such data and you're using it to actually look at patients who may not have the same level or problems of the same level of problems as others, you're actually doing so on potentially spurious information. So I think all of those are concerning.
Lizzie, you came to Google from 23andMe, right? And so you have people voluntarily giving information, but now we've seen whether it's the arrest of someone based on genomic data that was associated with their relatives, or other questions about use. Talk about some of the privacy and ownership issues that arise when you're working with these sorts of data.
Sure, and at first I'd just like to note that I think that when you think about data quality issues, when you think about representation in your training and evaluation data sets, how good you need to be depends on what you're trying to do. So it's not the case that we always need perfect data. We need to be able to measure how well we're doing. And in fact, then we tend to like to be as cheap and noisy as possible in the data that we get to solve that problem, as long as we're confident that we're going to be able to work with the data in ways that give us the actual, develop models that allow us to operate at the accuracy levels that we're interested in doing. Genomics is a discipline for which a lot of these topics ring true. One of the things that I think is actually fantastic where I sit right now, and we work mostly with publicly available benchmarking genomes that are developed by groups like the National Institutes of Standards and Technology and the Genome in a Bottle Consortium. So they pick very special people who get to have their genome sequenced following every single lab protocol we can think of on every single type of sequencing technology, evaluated with every single tool chain that exists. And they arbitrate all the differences to produce definitive, or as close to that as we can get, ground truth data. This is actually how we evaluate how accurate we are with genetic sequencing technologies. There's 3 genomes that are publicly available. One is from an individual of Northern European Caucasian ancestry. One is from an individual of Ashkenazi Jewish ancestry. And one is from an individual of Chinese ancestry. So even just with the first 3, there was a very explicit effort to have them be representative of multiple biogeographical ancestry is the term that we use in genomics, but whether it's race or ethnicity that ends up largely aligning with some of these things. Representation is critical when we look at the history of genomics research and thinking about who is going to benefit from the discoveries that have been made available through public investment. And is it conceivable that we can generalize beyond the populations that we studied? And in some cases, the answer is yes, and in some cases, the answer is no. And I think that there's much broader awareness that we need to be evaluating and validating these capabilities in the populations for whom we want them to have benefit. And in particular, we need to overinvest in groups that have been historically underrepresented. So the All of Us effort, which is what I think the Precision Medicine Initiative turned into, is explicitly focused on getting groups that have historically not participated in research involved. And I think this is a fantastic thing. Issues of ownership and privacy, I think, are critical. And I think that there's fantastic, deliberate discussion that's going on to talk about what are the things that are important, how do we enable people to have rights and control, while also recognizing aspects of public benefit that can come by making large-scale data resources available. What are the types of protections that we can put in place that make people feel comfortable how they're used? What are the levers that we can use to allow people to control their participation? But how do we also communicate some of the benefits that, quite frankly, a lot of people have derived value from because of a lot of research that people before them have participated in, and incentivize them and encourage them to be willing to allow their data to be used so that we can make more discoveries.
So Seth, you gave us an example at the very opposite end of precision. And I'm curious how, and that's the world we're in, so I'm curious how that actually plays out on the ground. I mean, if you don't know how many people there are in a city, how do you know whether or not you've been successful in delivering the immunizations you need to? You have funders who are looking for outcomes and results, and are they able to accept that level of uncertainty? I'm also really interested in whether or not the issues of privacy and confidentiality that we end up spending a lot of time at in conferences here come up when you're working in much lower resource parts of the world.
Well, it's changing. So, I mean, first of all, there are ways to validate. You can do surveys, and those surveys can get validated, and we can divide the world into countries that, you know, their administrative data looks pretty close to the survey data, and other countries where, I mean, Nigeria, we had coverage data of 105% and survey data of 33%. You don't have to be an epidemiologist to know there's a little problem there. So, in a sense, that helps us drive and where we want to work. But the interesting thing about the new tools is that they can be used to triangulate. So let me give you a different example. So vaccines need to be kept cold. So we have a cold chain, and that has to go all the way out to the periphery. Well, recently what we've done is worked with a company that has a wireless continuous cold chain monitoring device. They've worked with Google to put it up in the cloud. We've taken it forward in a number of countries. It gets really interesting because one, the simple thing is, okay, we know what the cold chain is and what's happening. But then you can begin to see temperature variations. And do those variations then predict failures of fridges? And if so, can you go in ahead of time and do preventive maintenance on those fridges or change the solar panels or do things to be able to make a difference? Now, where it gets really interesting is generally people don't worry about the same privacy levels as you see in the West. Stuff is pretty open. It's usually paper-based. And so as we move into digital, it hasn't been an issue. But all of a sudden, industry comes to us and says, hey, how come you're working with this company? We want this data because the data for this helps us work through our systems. And the challenge, of course, is when they want that data, they want to keep that data closed and not open sourced and not available to others. But of course, we want to get as much of this data and have it speak to each other so we can use it to predict and to work and to help everybody who can move forward. So I think it started out with the West being very closed, the South being very open. I think now we're going to see a shift in mindsets and behaviors. And a place like India is a little bit of both because they have a big industry, they understand the value, they want to protect their industry, they also want to collaborate with others. And so we're seeing kind of blended models going forward. So this is an area that is rapidly changing and will keep changing as technologies get rolled out in these places.
And as you were talking, I couldn't help but think, Jay, about your example of comparing performance across clinicians in very different settings. There's the data availability issue, but there's also the comparability and the acceptance by people of data coming from very different places. I would imagine it would be a challenge to get, I think your example was nurses in the US and physicians in the EU to believe that they should measure their performance against a community health worker in a poor part of the world. So how does, I'm just thinking beyond sort of data availability, the user's trust and confidence in the data seems very relevant to the enterprise you have.
Yeah, I think Lizzie made a good point earlier, which is there are things which are generalizable and there are things which aren't, right? And so there are going to be specific contexts or situations or cases that are going to be very disparate across different geographies. But at the same time, there are also going to be ones which are very actually connected and actually something that any physician anywhere, any health worker anywhere should be able to solve. And if we actually look at problems and we look at what are the biggest drivers of differentiation in problems, the two, I guess, are obvious in some ways, which is age and sex, right? And then from there are things like nationality and there are other things. But in many conditions and many situations, those actually are less relevant. So I think the key is if you have global baseline measures that are structured around information which is truly generalizable, I think that's where you have an opportunity to convince people that that's appropriate.
Guys, I mean, one of the interesting things, and Jay and I were talking about this earlier, is the competency model is important. What the goal would be over time is to try to upscale competencies to have lower level workers move into the next level and provide health services. The challenge is how do you make that comfortable? Now, I can say this as a physician, but doctors, of course, think only doctors can do things. But the truth is that most places in the world, doctors don't deliver care. It's delivered by lower level workers. But there is this kind of doctor mafia that says, well, no, you can't let nurses or community health workers give vaccines because it's too dangerous, et cetera. Well, the way to do that is to train, but then to have competency testing that allows you to say, okay, you're good enough to do that. And then if you can do that and you can particularly begin to compare across other places where you have good outcome data, then you've got a really strong argument why this is a more cost-effective way to deliver services.
And a small extension of that, which is really interesting, is if you can actually develop such measures in an effective way, you actually can empower the knowledge of pretty much any participant. So for example, imagine you have a diabetes patient who's lived for 50 years with their disease. They might know as much or more about the endocrinology of that disease as almost any clinician. And the reason that's so powerful is today we have no way of actually making use of that person's brain in a way that we can kind of say, yes, they actually do know as much about this specific topic, so we should weight their participation in the creation of such an information system accordingly.
Although historically, things like, the National Nurses Study, where you specifically recruit cohorts of people for whom you have an expectation that their self-reported data is of higher accuracy than it would be for the general population.
Yeah, and on the nurses one, we had our first day of internship. You knew the places you got your knowledge weren't from other doctors. It was from the chief nurse in the emergency room. So
I'm struck that in this conversation, you're talking about what some refer to as task shifting, and particularly the ability to use people with fewer skills to do things that we currently think of as requiring more skill. I know the example you gave was genomic sequencing, which is not something where there's you're not comparing a person to a machine because it's totally not possible. But you also work in the area of diagnostics where there actually are opportunities potentially to literally shift diagnosis out of the purview of a physician into the purview of a machine, that's quite different, and I assume brings up some fairly different implications. Is that something you can
Absolutely.
say a little more about?
So I focus on genomics, but my team overall is focused broadly. We pick up upon Google's mission statement, which is organizing the world's information, making it accessible and useful. So our lift is organizing health-related information and making it accessible and useful, in particular as relates to improving access and quality of care. And there are many, many, many parts of the world in which we have a significant shortage, whether it's of expertise or of bodies on the ground. And so we're very interested in ways that we can augment the current medical workforce. We have published work in looking at retinal fundus images and automating their interpretation for their diabetic retinopathy status. We're working in pathology, which is a discipline that is actually less digital, but opportunities to help pathologists who are reviewing digitized slides. We've also done work with medical records to synthesize information and make predictions about things that are likely to happen for a given patient. And in all of these, it's critical to understand who is your user, what are you helping that person with, what are they excited about, and what are they sensitive about in terms of introducing assistive technologies into the workflow.
So let's take that another step. Again, I'm just thinking even in the US, the resistance to moving functions that have traditionally been performed by higher trained, higher skilled, and higher paid people to those with somewhat less training. Jay, you gave the example of actually moving it to the patient, and if we move it to the machine, it seems very disruptive of our training models, our staffing models. You put a positive spin on it, which is you've got under-resourced parts of the world where this solves a problem. But I can imagine other places where it creates a battle because it's jobs and employment and prestige and the like. I imagine you come across this in talking about diagnosis, Jay.
Yeah, I think there's two things to remember here. So one is that in professions where there is a surplus of workers, AI is a far bigger problem than where there are shortages of workers. So for example, truck drivers. There are a million plus truck drivers in the US. So autonomous trucks could actually dramatically reduce their employment opportunities for such jobs. In the world today, we have 3.5 billion people who lack access to essential healthcare. And so we are not anywhere close to solving, and we'll talk more about this, I'm sure, what is almost a general intelligence problem of integrating multimodal data across scales the way that a highly capable clinician would do. So I mentioned this briefly in a prior talk, but when you're a physician, you're actually integrating so many levels and categories of data in a very complex multimodal way. Everything from symptoms and lab test data to genomics to proteomics to the microbiome to the social history of a patient, what type of society did they grow up in. Maybe in the future even, we'll look at how mitochondria process electrons at the quantum level. So there is a tremendous depth of information.
Did you get that, Seth?
I got it.
that has to be,
so did I. We're good. We're good.
that has to be organized. And because of that, integrating information across scales is really kind of the nature of general intelligence. It's having a knowledge of the state of the world and many different categories of information. So we're very far from a place where, AI generally threatens the specific jobs of health workers. But the final point I'll make is that the benefit here is that if we can up-level every person in the system, we can take a primary care physician, give them some of the powers of a specialist. That's what an e-consult does. Or we can take a nurse practitioner and give them some of the powers of a primary care physician, all the way down to a patient and giving them some of the powers of a community health worker. That's actually how we get to universal access to care.
This is a very positive image, and I don't want to burst the bubble, but I do want to raise the question because we've used some examples where you're stretching, extending where there are insufficient resources. We had a paper about a year and a half ago that talked about the diffusion of advanced genomic sequencing for cancers, and it was a very interesting method. I won't go into the details, but it really did show that the diffusion within the US of that technology was very much related to income disparities within the community, that higher income communities, you saw faster take-up. So here's this potential technology, life-saving, that has, in the first instance, seems to actually increase inequities in health rather than decrease. Now, maybe somewhere down the road you get to the tail of the curve and it becomes available to everyone. But I'd like you all to step back and ask sort of where are the investments in these, I realize it's a very broad question, where are the investments being made in this kind of machine learning, artificial intelligence, relative to where the problems are? Are we following the problems or are we following the money? Simple question, who's gonna?
I'll go first with this one. We are at an interesting point, we, both specifically and broadly, we have, to date, I think, been convincing ourselves that this works with very selectively chosen examples that were somewhat opportunistic in nature. These data sets existed already. We have wonderful genomic data. There are retinal fundus images if you go to the UK Biobank. They've done this for their entire cohort. And that makes sense as a place to start, to convince yourself that this methodology works, that we can hook it up. You inflect once you've convinced yourself that it works to think about what you want to do with it. And that circles back to these questions of what are the problems that we want to solve and what are the data that we would need to solve them. And in some cases, we have a pretty good sense of what the data are, but maybe we weren't optimal in our methods of collecting them. In some cases, it's actually unclear where the strongest signal that will come from that we're interested in. And it might be a traditional collected in a brick and mortar clinic signal. It might be something that we can get off of your cell phone. These are open questions that I think are really exciting to think about more. And when we realize this is what we're interested in making an impact on, then the question becomes how. And there, I think, is a really key. If you continue to be opportunistic in nature using the data that are already available, I think you have the biggest risk of, at a minimum, persisting health disparities and inequality, and worst case, worsening them. We have very little chance of making them better. But if you are eyes wide open to the possibility that that happens and you make informed choices, and in fact, if you make investments to focus on the problems that you want to solve for the communities that you're interested in impacting, then I think you have a chance of doing some good.
Seth?
I actually think it's really interesting because right now, given the early stage, you know, what you've heard is exactly right. But what we're learning more and more about technology is how developing countries who want to can leapfrog over what the West has in technologies. I mean, it's not so long ago, Mo Ibrahim was saying, you know, we need cell phones in Africa. People are like, there's no business model. People don't have any money. They can't eat, blah, blah, blah. A few, you know, $1 billion later. But what's interesting, a place like Kenya, you know, the M-Pesa, they do their banking on mobile phones. It's now 45% of the GDP. And, you know, we worked with a company whose CEO is here on a drone-based delivery system for health products. Turns out you try to do that in the US, you got to deal with the FAA, you got to deal with state regulations, all this kind of crazy stuff. There, they were able to get quick approval, they were able to iterate and be able to show the technology works. So those are 3 examples of technology, not necessarily AI and machine learning, but there may be a way, given the privacy concerns, regulatory issues, and others, where some smart entrepreneur can say, let me focus first in the developing world, build that experience, prove the value of it in a faster and easier way. And when we've discussed that with funders, for the first time, you begin to get funders to say, hey, maybe this business model makes sense. It isn't always going to the richest, you know, wealthiest people first, but rather going to places that need it most and that will really appreciate it.
Yeah, so in general, advanced technology, the opportunity to use it for social change is most effectuated by organizations that have large amounts of capital and can retain that capital over long periods of time. So, for example, you know, classically Xerox PARC, or now what Google's doing, or you know, all of these research labs that can kind of take very long-term ambitious bets. Governments, foundations, et cetera, can support this type of work. The issue is that if you're a smaller organization, you have to make the economic incentives work or you don't survive. And the real problem is that, that the way that economic incentives work are really what enable data network effects that actually enable and empower many organizations to join around a given intervention, right? So if you have a specific AI solution, unless the incentives are aligned, no one's going to get on board. So this is a classic example, like Google Health was this early example of where there was this tremendous idea of kind of putting all this information online and putting electronic health records online, but there was no why. There was no reason for patients to actually do it because there was nothing that they were getting out of it. So unless there is a real incentive for the stakeholders who are involved, you don't get the network effects necessary to actually make a technology really successful.
Can I add one more thing, which is, so our genomic tool is, at its core, leveraging an image classification technology that Google developed called Inception. And it started off with Google engineers trying to figure out, is this a picture of a cat or is this a picture of a dog? Which turned into this generic image classification model that can be retuned, we call this transfer learning, to specific applications. This is what we use for our variant calling algorithm. This exact same open source, publicly available model has been reused by multiple third parties, including small, low resource groups. One recent example that I particularly enjoy is a group that is based out of Penn State University working in country in Tanzania to develop a model that exists on cell phones that lets farmers take pictures of their cassava leaves and diagnose whether those leaves indicate that there's any type of disease present, and if so, give them resources. This is a big problem locally, where this is an incredibly important staple crop, and it's a challenging thing for your typical farmer to do. This is actually the same core technology, and the fact that you're 95% of the way there with publicly available tools that actually don't require a tremendous amount of technical expertise to be able to use, I hope, will allow more groups to reap the benefits.
And that's a big idea, because the thing is that it's one thing to say, okay, cassava. You're not going to see research institutions in the United States from an economic point of view be interested in cassava. We don't eat it in the U.S. It's not a crop we're going to sell, but it is a staple crop in these countries. So here's using a technology developed for something else, now adapted to be used in a place that wouldn't necessarily have an economic model to create their own tool, but can make a huge difference in that. And that is exactly the type of crossover. It's a great example.
Okay, before I turn to you, I'm going to ask each of you, we're back here 5-10 years from now, we're having this session, I ask you, what's the most exciting thing that's happened in the last 5 or 10 years that's moved us forward in our ability to deploy these technologies to improve health? And maybe we'll do it, but whether we're going to do it or not, we want to know what you think you'd say. Jay, where do you think where are we going with this?
Yeah, no, I think there's a lot of interesting places this could go. But the thing that excites me the most is the extent to which such technologies can empower a more distributed, integrated virtual care model, right? So as more and more care gets pushed to the edge outside of existing care settings, that's how we can dramatically reduce costs while also keeping outcomes the same. So, we talked earlier about some of Zipline's work using drones for blood delivery to sites all over Africa now, Rwanda and Tanzania and many others. That's one example, but as a simple example, which is a question I asked in the last session, most of the people in this room probably haven't even used a telemedicine visit. Most of us haven't used home care or aging in place, for our parents or family members. And that is really the place in which the intersection of data analytics and AI can actually extend the capacity of care to more types of people in more types of care settings to radically shift the cost curve in the next decade.
So you all know about what the Sustainable Development Goals are. One of those development goals, 16.9, is actually having everybody have an identity by 2030. We can do that today. We can use interesting things like digital ID with blockchain to be able to give people identity and then attach information to it. I would like to see that happen, because then we could vaccinate every child on Earth when we know where they are, and plus make sure that they have a life going forward where they can own property and do other things.
So my answer to this question is actually different from all the examples that I've used so far. So yesterday I sat in the audience in this tent and listened to a session on physician burnout, suicide rates, substance abuse, churn from the field. Now, some of the doctors that leave medicine come to work with me, and I think that's a good thing, because it helps us make tools that are actually going to be used by doctors. But one of the things I'm actually most excited about and think has an opportunity for very near-term translation into use is thinking about ways we use the phrase bring the joy back to medicine and alleviate some of the documentation and workflow burdens that are on clinicians today by repurposing some of our existing technologies that Google developed for things like the Google Home, things like speech recognition technologies that might be able to let doctors do what they were trained to do and not do the things that they really do not want to spend their time doing. And I assure you, they have no concerns about that type of technology being deployed in their clinics.
Very good. Okay, we have a few minutes. Let's get a microphone to you so you can identify yourself. Let's take it right back. Okay, here on the aisle, right here.
Hi, Remley Newton-Dame. I do analytics in a safety net system. And my question's really around, as these technologies come out and are practiced outside of sort of the academic medicine world, how do we get the workforce in the kind of rank and file places to be able to take up the kinds of tools that you're building and give them to the patients who need them most?
I'm happy to go first here.
Sure.
So I mentioned that we're working, one of the capabilities that we've developed is able to take a retinal fundus image and evaluate it for its diabetic retinopathy and diabetic macular edema as well. Those are actually being deployed in clinics in Southeast Asia in clinical validation settings. And we were explicitly interested in this one because these are the settings where there are no experts available. And this is one of the leading causes of blindness in many parts of the world. So we sent teams, we do a tremendous amount of human-computer interaction work, which is understanding what are the technologies that you're using today, what does your physical space look like, what does your workforce look like, and how do we ensure that this works for you in a clinic that might have inconsistent connectivity for your internet, or this is how much you can pay for a camera. So we're very mindful of that. In the US, there's tremendous differentiation in the types of facilities that administer care. And I'm personally very aware that the vast majority of this care doesn't come from major academic medical centers or from major tertiary care centers. And we have to be mindful of that when we are evaluating how things work and how they would need to be packaged in particular and who needs to be trained on how to use them. I think it's a great point.
So we roll out digital tools in the developing world, and as you can imagine, people are really keen. The biggest problem we have there is that initially that's not trusted. So what it is additional work because then they also want to have the parallel system set up on paper and digitally. So the challenge is getting to that leap of faith that allows you to then jump off and just use digital, including all of the advantages and tools you can use with rapid feedback, et cetera. So, and only a few countries have done that, but as more do that and as people get more comfortable, it will accelerate.
Unless, Jay, you want to jump in, let's take a question right up here in the front. Try to get two more in before the clock runs out on us.
So I know you mentioned that the result of the Google Genome Project was released online and is now open source, but I was curious how common that is. Normally when companies come up with these blockbuster algorithms, do they look at patent options? Do they remain trade secrets, or is it fairly common for them to be released to the public?
Yeah. It's a fantastic question. So there's sort of what's normal, and then sort of what is our position on that. We have seen, and we actually didn't talk a whole lot about big data, but one of the reasons that we're seeing a lot of these technologies be broadly used is because it's possible to work with much larger data sets because of different types of computational accelerators and larger scale data storage capacity. So all of our data that we used was public data. And as of a couple of months ago, some of these accelerator types for compute are publicly available. So whether we tried to protect that, someone could just go and reproduce it. And so I think that I'll also note our goal is actually, my team's goal is actually to infuse bioinformatics with deep learning. And to do that discipline, they will not trust a black box solution. They will not use it. They need to be able to open the hood, see how it works, and trust it for themselves. But I think we also believed fundamentally that it was the right thing to do. Our objective with this was not to make money off of this tooling. You can run it locally. You can also run it on Google Cloud if you want to, and there'll be some type of storage or compute costs associated with it. But that wasn't the motivation, and I think I'm very privileged to work in an organization where I have to ask a couple of people for money. I don't have to go spend a lot of my time. And I frequently can convince them that this investment has a much better long-term payoff for the larger scale goals that we're trying to achieve. But I think this is critical of, is there really something protectable? And is this essentially trivially reproducible by the public, given some of the publicly available tools?
So I know you asked that of Lizzie, but Jay, I am curious, because you're in a big data gathering enterprise as well, what you experience in terms of ownership of algorithms and the like.
Yeah, the short answer is when you're thinking about IP, it doesn't make sense to have IP around things that are not easily verifiable. So with respect to the use of technologies that you would typically do on your back end and not expose necessarily, you wouldn't have an interest necessarily in protecting those with IP versus with trade secrets. Now, on the other hand, I think the key point, and perhaps the most important point here, is that the quality of algorithms is highly commoditized because the research ends up growing very quickly to better solutions, and a lot of that ends up being publicized. The key is really the quality of the information going into such systems.
Interesting. Got the gentleman here in the front, and I'm keeping an eye on the time. We'll see what we can do.
I'd like to build on I'm Dave Neer here with the Annenberg Center for Health Sciences. And we're a CME provider, so we're concerned with expanding the knowledge base on the clinical practice of medicine and hopefully beyond the clinical practice. But my question, building on the previous one, and if you think you've answered it, I guess you can just say that, but it's specifically with the process and the methodology with which these algorithms, which will be increasingly used as tools in the clinical delivery of care, are developed. You know, today, the clinical knowledge base values, in fact, insists upon an open scientific process where you have a finding and you publish it and it's replicated before it becomes part of the evidence base and best practices and so forth. But in my conversation with one of the leaders in the area of machine learning and artificial intelligence tools for the clinical practice of medicine, it was very clear this is proprietary. This is our intellectual property and we would not disclose that. So is this something that we should be concerned about? If so, how do we approach it? Is clinical care going to go the way of patent protection like we see in devices and pharmaceutics? Or is this not something to worry about?
That's a fantastic question, and actually was the topic of the big idea presentation that I had at the beginning of the conference, which is we need hundreds of open intelligence systems that can be understood, that can be audited, that can be inspected for how they work, for how they're used. In the same way that we have Linux in addition to Windows, we should have the same in healthcare and really in any intelligence problem. We should actually be able to understand more of the nuance of how these systems make decisions.
Let's get one last quick question in if I can. Actually, let me take it back here if I may, sorry. But the microphone is closer and we don't have much time. So.
Hi, thank you for this timely talk. So my question is about even the best of intentions and development initiatives can have oftentimes catastrophic consequences. And I'm wondering, Jay, you had mentioned incorporating experiential expertise. Lizzie, you had focused on or mentioned targeted investments. I'm wondering, how do you incorporate local voices into the innovation pipeline, development, and a determination of what questions get answered and where the money goes when you're coming in as a representative of Google with the purse strings, the power, and the politics behind you?
Simple question to end on.
This is a fantastic question. And I think I'll touch upon a couple of points in answering. One is, I come from Google. I've been there for 8 years. There's a lot of things that Google is very good at. It dabbled in health, as mentioned earlier. The original Google Health effort is no longer, and we can do a postmortem on that some other time. I am very aware, and I think that my colleagues are as well, that we can't make traction in health broadly, and in particular in healthcare, just using the people that Google normally hires. We will have a reasonable likelihood of convincing ourselves that this makes sense, and it will be something that is just not appropriate because there's so many things that are custom about health. And so we hire many people, we consult with many people, we engage with people who are representative. My training came actually out of community-based participatory research. I'm very, very aware of the importance of deeply understanding the interests and the considerations of the communities that you're working with, and recognizing that frequently you don't operate with the same definitions of the same words. And you have to do an overabundance of communication to really understand what people are interested in and why they're motivated, and what you care about and how to get those things aligned. You mentioned something about sort of catastrophic potential consequences. I think this is something that people are thinking a lot about right now. Google actually just published, for the first time, ethical principles in the use of AI, not in a healthcare specific manner, but that will infuse all of the company's efforts. I think this is a great starting point to establish some reference for conversation. There's a balance to be struck between protecting ourselves against potential abuses and stifling the innovation that might have tremendous positive impact.
Jay, you want to?
Yeah, I mean, that's part of the reason, I don't know if this is still working. That's part of the reason we're building the Human Diagnosis Project as an open movement that's actually created with and led by the medical community. So 10,000 physicians from 80 countries, much like open source software like Linux is created by 14,000 engineers from all over the world. And that's kind of the heart of it, but the second piece of it is looking at the world from a stakeholder lens instead of a user or customer lens, which I think is very common in tech. And so we kind of think about all of the major communities which the work touches. So one is obviously the medical community, and as you pointed out, has workforce implications. The second is the open source technology community. The third is the scientific and research community. And the fourth is obviously the patient community and the general public, people who aren't yet sick but might be. And so to your point, I think you need to include all of them in building such systems to ensure that this is done in an open, inclusive, co-creating sort of way.
And even abstracting from AI and big data, that's certainly your experience with getting vaccines into the hands of people around the world. It's about local engagement and participation. Well, I hope you agree we've had a robust discussion of the potential, the opportunities, the challenges,